Good morning. We are back and better than ever. We are talking about operations with plain vectors today. Addition, subtraction, and multiplication is what we're going to talk about. Very simple, very straightforward, but we're going to show you why we can do what we can do with the vectors when we add, subtract, and multiply. So, geometrically, we've been adding vectors, like the vector A plus the vector B equals A plus B. So we start from the starting point of the first vector and we draw our vector to the ending point of the second vector, or the last vector if you're adding or subtracting more than one vector. And what are the final components of the vector A plus B? Well, if vector A has components A1, A2, and remember, this is horizontal and this is vertical. When you're in component form. And B has components B1, B2. If I start here and I want to end up here and I'm just going to move horizontally and vertically, I'm just adding the horizontal components, A1 plus B1, to get directly under the final, the ending point of the second vector. And then to get up to that point, I'm just adding the vertical components. So A2 plus B2. So to get from here to here, I go right A1 plus B1 and up A2 plus B2. And that leads to this nice formula, which is not on your formula sheet. If I have two vectors, A and B, to add them, I just add their corresponding components. Very, very simple, very intuitive. So here, very simply, if I have to find A plus B, vector A plus vector B, it's simply equal to 1 plus 4, the sum of the horizontal components, and the sum of the vertical components. So this turns out to be 5, 4. So we're going to prove that geometrically, and we'll start with the vector 1, negative 3. So I can start anywhere. So I'll start at this point. So 1 is 1 unit to the right, negative 3 is 3 units down. 1, 2, 3. See if I can get the arrowhead right or close to it. That's about right. So it's supposed to be down here, so we'll start from there. And that is vector A. Okay, so now from that point right here, we're going to add to A vector B, and vector B is 4, 7. So I'm going to go right 4, 1, 2, 3, 4, and up 7. Oops, got to start over. Go away. Okay. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So there we are. Okay, so then that should be about there. Sorry about that. So this is vector B. Okay, and then the final vector, or the vector A plus B, we'll put in red. Goes from the starting point of vector A to the ending point of vector B. It should be at that intersection. I apologize for that. I'll do the best I can. Not bad. This is the vector A plus B. Okay. Well, what are the components of A plus B? How do I get from here to here, moving only horizontally and vertically? Okay. Well, let's take a look at that. We'll make this dash just to have a little fun here. So we're going to start from A, and I'm going to end up moving 1, 2, 3, 4, 5 units to the right, and then 1, 2, 3, 4 units up. So we've just shown geometrically that, again, the vector A plus B has the components 5, 4. Okay, onward. Negative vectors, very simple. If I have a vector A equal to 2, 3, and I negate it, it becomes negative 2, negative 3. So here's vector A, 2, 3. If I negate it, it's -2, -3, and that makes it go in the opposite direction. Same length, same magnitude, just opposite direction. So we're just verifying the operations are the same when we're doing normal addition, subtraction, multiplication. Vector subtraction. Again, what this is showing, and we've already done it geometrically. If I have two vectors A and B with these components, if I take A minus B, I just subtract the corresponding components, A1 minus B1, A2 minus B2. So let's do an example real quick. So vector Q minus vector P is going to equal 3 minus 1, -2 minus 4, which is going to give us 2, -6. And then P minus Q minus R, okay, that's no big deal. See, P is going to be, I could just use this as, oh no, this was Q minus P. Holy smokes, I totally messed this up. Let's redo that. Q minus P is going to be 1 minus 3, 4 minus a -2. Sorry about this. So that is going to be -2, +6. Didn't read the direction. Let that be directions. Let that be a lesson to you. Okay, so P minus Q minus R is going to be 3 minus 1 minus a -2. And then for the vertical component, -2 minus 4 minus a -5. And that is going to equal 2 plus 2 is 4. -6 plus 5 is -1. So there we have it. Okay. And what about multiplication? We've seen it geometrically already. If we multiply vectors, we just have to multiply through by the coefficient. In other words, if I have a vector v that has components v1, v2, and I multiply by some constant k, I just multiply the constant by each of the components, by the horizontal component and by the vertical component. If I multiply by -1, we've already done this, everything becomes negative, it's the negative vector. If I multiply by 0, it becomes the 0 vector. Okay, so 3q, let me get rid of those, sorry. 3q is going to be 3 times 2 -3, which is simply going to be 6 -9. And I'm just going to skip to C. This is very simple. So 1/2 P, so that's going to be 1/2 times 4, 1, minus 3Q, so that's going to be 2, -3. So that will equal, let's see, 2, 1/2. Let's see, minus, I'm going to leave the minus here and just multiply by 3. 6, -9. So we have 2 minus 6 is -4. 1/2 minus -9 is 9 1/2. And what about this? If P equals 3i minus 5j and Q equals -i minus 2j, find the magnitude of P minus 2Q. So P minus 2Q, that's going to equal 3i, remember these are the unit vectors I and j, minus 5j, minus 2 times -i minus 2j, which equals 3i minus 5j plus 2i plus 4j. You know, we're using unit vector notation. The rules are not any different. I can just, it's like combining variables. 3i plus 2i is 5i, and -5j plus 4j is -j. So that implies that the magnitude of P minus 2Q is equal to the square root Remember, this 5i is 5i, let's just make sure we understand what's going on here, is the vector 5, 0, because it's 5 times the unit vector 1, 0. And j is simply the unit vector 0, 1. Okay, so this becomes 5 squared plus negative 1 squared, which is the square root of 26. That is it. I am out.